All right, we're still in AP Stat. We're still in Chapter 6, just trying to go over some practice problems so you can see how all this stuff works out. So this is Chapter 6 in Unit 1, finalizing this, and I have some a summary of practice problems and some review sections for you as well. But anyway, if I'm moving too fast, pause these videos. All right, write the problems down. I have to move faster. It will take forever to get through everything. Okay, so take a look at this problem. Each year, thousands of high school students take either the SAT or the ACT standardized tests, and the colleges use them to help with admissions. So the combined SAT math and verbal scores go as high as 1,600, while the maximum ACT score is 36. And since the two exams use very different scales, comparisons of performance are difficult. A convenient rule of thumb is the SAT equals 40 times the ACT plus 150. That is, multiply an ACT score by 40, then add 150 to estimate the equivalent, to kind of compare the two, I guess. An admissions officer reports the following statistic about the ACT score of 2,355 students who applied, and find the summary. So basically what they're saying is, we got the low, right? We got the standard deviation, we got the mean, we got the quartile, right? We got interquartile range, the median, right? We got all this. So as you're looking at this, it says, find the summaries of the equivalent SAT scores. So when you're doing this, the measures of center and the position, right? The lowest score, top 25% above mean, and will be multiplied by 40 and increased by 150. So what we're saying here is, if you take these scores, these ACT scores, right, that we are given, what we're supposed to do is we're supposed to take the score, and then we're supposed to, we'll multiply it by 40 because everything gets multiplied by 40. Okay, so we want you to do multitude of things to it. But keep in mind, then you add, but you don't change everything with adding, right? You only change when you're adding. You're only changing the ranges. So the interquartile range, standard deviation stays the same. Sorry, they will stay the same, but everything else will have something added to it. All right, so just things to think about. So the example here is, if I take this 19 and multiply it by 40, then I add 150, I will get this. The same with the mean. Okay, same with the median, same with all that. But the point is, with this right here, these aren't going to change. Notice how I just take this and I multiply it by 40. That's it. Take this and I multiply it by 40. They stay the same. So it says, when you're doing this, an admissions officer reports the following statistics about the ACT scores of this and who would apply. Find the summaries of the equivalent SAT statistics. So there you go. Top 25% or above. That is right there. So it took the 30 and altered it. A high school senior uses the internet to get information on February temperatures in the town where he'll be going to college, and he finds a website with some statistics, but they are given in degrees Celsius. The conversion formulas are as follows. So determine the Fahrenheit equivalent for each of these. So now this is the same idea. You have your max, you have your range, standard deviation, mean, median. So this idea is to take someone else's statistics, but you need to morph them into your own. You don't just plug it in the formula and everything switches. Again, the ranges stay the same. Interquartile range will stay the same. Standard deviation will stay the same after you multiply it. But the adding, the max temperature, and the mean and median are all that will change. So that's basically what we're elaborating with when we go over this, and this is what we'll get. So notice that I will take the 9/5 times everything, but the range isn't going to change. If you take 33 and you multiply it by 9/5, all right, I get that, and I'm done. Take the standard deviation times 9/5, take the interquartile range times 9/5, that's it. These, however, then I need to add the 32 to it. So if I take that 11 degrees Celsius, times it by the 9 over 5, all right, I would only get 19.8. I have to add the 32 to it in order to get the 51. Okay. Suppose your statistics professor reports test grades as Z-scores, and you got a score of 2.2 on the exam. And it says write a sentence explaining what that means. Okay, so you need to take the 2.2, which was your z-score that you got, and then rewrite it. So a 2.2 means that your score was a 2.2 standard deviations above the mean, is what that means. Your score was 2.2 standard deviations above the mean. That's what it means. Simple. Like there's nothing else to do. You could try to convert it, but you're going to have to know more information in order to try your best to convert it to your actual score. Like, what is the mean of the data? What is the standard deviation of the data? But you know that you must have done pretty well in conjuncture to what the mean was. So keep that in mind. The average score that everyone got on a test could have been like a 13%. You just did better than them by over 2 standard deviations, that's all. But you could have still failed the test. One of the authors has adopted a grandson whose birthday or birth family members are very short. And after examining him at his 2-year checkup, the boy's pediatrician said that the z-score for his height relative to American 2-year-olds was this. So that just means, again, that a z-score of that means that the boy's height was 1.8 standard deviations below the mean. That's all. It's got to get you used to understanding what these terminologies mean. The mean score on the SAT exam was 75 points. That was the mean score on an SAT exam with a standard deviation of 5 points. And it says Gregor's z-score was -2. How many points did he score? So you set this up by simply saying, okay, so I know his score, and I know the average was 75. I know that is 5. I know the -2 is the z-score, so I plug it all in. I multiply by 5 and add that to figure out that Gregor basically got a 65, is what he did. People with z-scores above 2.5 on an IQ test are sometimes classified as geniuses because they're 2.5 standard deviations above the mean. And if IQ scores have a mean of 100 and a standard deviation 16, all right, what IQ score do you need to be considered intelligent? Well, 2.5 standard deviations, you could roughly eyeball this. That's 1, 2 would be 32, and then half of that about 40, so maybe like 140. Now, I just eyeballed that by going up 1, then another, and then half of that. But what you could have also said is 2.5 goes in there. The mean is 100. 16 is the standard deviation. So you multiply by 16 and add 100 to get anything that is 140 or above would be classified as being a genius. An incoming freshman took her college placement exam in French and mathematics. In French, she scored 82 and in math an 86. The overall results on the French exam had a mean of 72 and a standard deviation of 8, while the mean math score was 68 with a standard deviation of 12. On which exam did she do better? Right? Because comparatively speaking, you look at it and say, ooh, 82, but comparatively to everyone else who took that exam, how did she do? So the point is, on the French exam, the mean was 72, and the standard deviation was 8. And she scored that. The student's score of 82 was 10 points, or 1.25 standard deviations above the mean. Because what you would basically say is, I know the average, I know hers, so 82, you take that 82 that you know she got, and they said the average was 72, and the standard deviation was 8, so basically you subtract them and divide by 8 to get 1.25, and it is above the mean. On the math exam, though, the mean was 68 with a standard deviation of 12, and she scored an 86. So you take that 86 that she got minus the 68, and then divide by the standard deviation of 12, and she got 1.5. The student's score of 86 was roughly 1.5 standard deviations. So technically, yeah, her score was higher on the math, but she actually did even better than the 82. Not just because the score is higher, but because it was 1.5 standard deviations above the mean. Combining test scores. The first stats exam had a mean of 65 and a standard deviation of 10 points. The second had a mean of 80 and a standard deviation of 5 points. Derek scored an 80 on both tests. Julie scored a 70 on the first test and a 90 on the second. They both totaled 160 points on the 2 exams, but Julie claims that her total is better. And explain, why would that even be possible? Well, the z-score, which account for the difference in the distributions of the 2 tests, are 1.5 and 0 for Derek, all right, and 0.5 and 2 for Julie. Derek's total is 150, which is less than hers, which is what she's getting at. So the point is, when totaling this up, what we're saying is the first stat exam had a mean of 65, standard deviation of 10, right? And he scored an 80. So you would take that 80 minus 65, divide by the 10. That's why his first test he was 1.5. And a standard deviation of 5. Derek scored an 80 on both tests, though. So the second had a mean of 80 and a standard deviation of 5, so it would be 0. So if he was right on the money, and then he's a little above the money on those. Whereas with Julie, she did it, same idea. Julie scored a 70, which is still above the mean, and then she scored a 90, which is more above the mean, and she got standard deviations of 1.5 and 2.5. All right. So, explaining, is it the same one? Oh, different person. The point I'm getting at is the reason why she's saying it's better is if she took both of those z-scores and put them together, even though they both total the same amount of points, she actually has a better z-score with both of them when you add them all up. It's basically all it's just saying. 1.5 and 0, he was basically only 1.5 standard deviations above the mean, whereas Julie was 2.5 standard deviations above the mean if you total up both of them, would be her explanation. I'll stop there. When we come back, we can dive in to some more practice problems.